Alrighty, good morning, everybody. Thank you for being patient with me. I burned some sausage here this morning, so I had to spend a few extra minutes airing out the house and turning off the smoke alarms and all that fun stuff. So I do apologize for running late, but today is going to be a fun day for us. On Monday, we talked about exponential functions, specifically how compound interest led to the discovery of the number e, and how that number e is very special as a base for exponential functions, sometimes called Euler's number, sometimes called the natural base. And then at the very end of class on Monday, we sort of tried to motivate the study of logarithms as the inverses of exponential functions by talking about the path to solve the equation 2 to the x equals 3. We were able to see from the graph that that equation 2 to the x equals 3 must have some solution. And then I just kind of pulled one out of my ass and convinced you, or tried to convince you, that it was, if not the exact solution, at least very, very close to the exact solution. Today, among other things, I will show you the exact solution to that equation. I'll show you where it comes from and the notation that's used to communicate it. And we'll discuss more generally the types of functions that output solutions to those equations, which are called logarithm functions. So you may recall I was suggesting on Monday that you spend some time reviewing the concepts behind inverse functions. And that's because logarithms for us are going to be defined as the inverse to an exponential. Okay. Let me turn on the document camera and we can take a look. I did get a couple emails from people saying that they needed their tests last night, and I was able to get those out. I know that a number of you are still waiting on those, and I appreciate that. They will be in shortly. So this is MAC1140, section number OR1, which is pre-calc. And today is the 3rd of November, 2021. Today we will be talking about logarithm functions, which is section 4.3. And that's just logarithms. Okay. So last time, we saw, among other things, that the exponential function f of x equals 2 to the x has an inverse, and we sketched the graph of that inverse inverse of x from the graph of f of x. I'll remind you what that looks like. Nice picture in here with lots of points labeled. It was at the very end of class last time. Okay, so I'll tag this as like 1, 2, 3, 4. One, 2, 3, 4. And -1, -2, -3, -4. So the graph of 2 to the x, of course, goes through 0, 1, 1, 2, and 2, 4. It also goes through -1, 1/2, -2, 1/4, and it approaches this horizontal asymptote over here, something like this. All right, so this is the graph y equals 2 to the x. Or I'll write it as f of x equals 2 to the x. And remember, the way you get points on the graph of the inverse from points on the graph of the original is to flip those points over. So this is 2, 4, 1, 2. That's 0, 1, of course. This is -1, 1/2, and -2, 1/4. So if I want to graph the inverse to this function, you would have on him the point 4, 2, because I flip this 2, 4 over, and that gives me 4, 2. You would have on him the point 2, 1, because I take this 1, 2 and exchange x and y. So that's 2, 1 right there. You would also have the point 1, 0, because 0, 1 is on the original. You would have the point 1/2, -1, because -1, 1/2 is on the original, and you would also have the point 1/4, -2. So the inverse function, whatever that is, has to look something like this. So this is the graph y equals f inverse of x. And it turns out that this inverse function has a name. The inverse of the function 2 to the x is called log sub 2 of x. That's the name of this function. And I'll explain what all of this means. Here's the definition. I'll put it in purple here. It's not a solution to any problem, but I'll put it in purple to match it with this. The inverse, and I'll give it in general, to the base a exponential f of x equals a to the x is the base a logarithm f inverse of x equals log sub a of x. All right, this is the definition of the logarithm. So logarithms are the inverses to exponentials. If you have 2 to the x, the inverse of that is the base 2 logarithm, or log sub 2 of x. If you had 10 to the x, the inverse of that would be the base 10 logarithm, or log sub 10 of x. So this number a right here, the base of the logarithm, is the same as this number a right here. So this a and this a are the same thing. This guy and this guy. So this guy right here, the purple graph above, is the base 2 logarithm because he's the inverse of the base 2 exponential. 2 to the x has base 2, so his inverse is the logarithm with the base 2. I want to show you or describe some of the features here. So the domain of f here, the domain of the original 2 to the x, is all real numbers, negative infinity to infinity. And the range of the original, I'm color coding this, this is for the black graph, is from 0 to infinity. And of course, he has a horizontal asymptote, y equals 0. The corresponding information for the logarithm, the purple function over here, remember the way this works. The domain of the original function is going to be the range of the inverse. So over here, I'll just write domain, range. So the domain of the original, the black, all the x values you see there, is the range of the purple, all the y values here. So since the domain of the black is negative infinity to infinity, the range of the purple is the same, negative infinity to infinity. Remember how we get the purple? We switch all the x values and y values on the black, right? So every x value that's on the black is a y value on the purple. Well, all of those x values, that's the domain. And all of those x values become y values on the purple. So the domain of the black is the range of the purple. And the same is true of the range of the black becoming the domain of the purple. All of the y values on the black become all of the x values on the purple. So the range of the original is the domain of the inverse. So the domain of this logarithm is 0 to infinity. The horizontal asymptote for the black, this is not as obvious, I think, but it takes a little bit of thinking. If you take all of these points on this curve and you reflect them over the line y equals x, this horizontal asymptote is also going to get reflected over that line to become a vertical asymptote for the logarithm. So the logarithm here has the vertical asymptote x equals 0. This is the general picture for the graph of a logarithm. The domain is always going to be 0 to infinity, right? If you just have log base a of x, any function like this, log base a of x will have domain 0 to infinity, range negative infinity to infinity, and vertical asymptote x equals 0. I mentioned on Monday, in a sense, the exponentials are much nicer than the logarithms because it's very hard to upset an exponential function, meaning like you can plug whatever you want in here and it won't get angry at you. But if you try to plug 0 in here, or if you try to plug any negative number in here, then this thing will get upset at you. Right? The domain is just 0 to infinity. You can only plug positive numbers into a logarithm. There's actually kind of 3 equivalent ways to define the log, and we're going to get to all of them. What I'm going to show you next is just sort of a recharacterization of this original and inverse statement. So remember what it means for 2 functions to be inverses. It means this should exactly undo this. So if you take a number and plug it into f, and then you take that output and plug it into f inverse, you should get the number you started with. Another way of saying that so we'll call this an alternate definition. The base a logarithm is defined by, say, log sub a. Right, this is the function here, is defined by the rule if the base a log of x is equal to y, that is equivalent to saying that, let's say this y, let's say x, yeah, we'll say this x is equal to a to the y. And if you think about it, the purple definition and the black alternate definition say the exact same thing. There will be times when it's useful to think of logarithms as inverse functions, and there will be times when it's more convenient to think of them like this. For most of today, this bottom definition is going to be the more convenient one. So you can take any statement about logarithms and rewrite them as a statement about exponentials. You can take any statement about exponentials and rewrite them as statements about logarithms. I'm going to make a little note here. The number a is the base of an exponential. So when you're talking about the logarithm here, base a logarithm, we're still assuming that a is positive because that number a is the base of an exponential. You can always assume that the base a is greater than 0. You'll also never see a equal to 1 because then this would be a constant function, but that doesn't really ruin anything for us. It's just not as exciting. So the first thing I think we need to do in order to get comfy with these things, besides having some clue what the graph looks like, the domain and the range, is to take some statements and write them in both exponential and logarithm form. So we're just going to use this blue box statement here to go back and forth from something that looks like this to something that looks like this, and vice versa. Okay. So here's what we're going to do. Let's take the statements 10 to the 5 equals 100,000. We're going to write all of these in logarithm form, meaning we're going to take this exponential statement and rewrite it as a statement about logs using that blue box. 2 cubed equals 8. 3 to the negative 2 equals 1/9. And e to the 0 equals 1. Each of these is a true statement, right? 10 to the 5 is 100,000. 2 cubed is 8. 3 to the negative 2 is 1/9, and e to the 0 is 1. There's nothing to solve for here. But I can rewrite each true statement about powers as a true statement about logarithms. So I'd like you to take a look at that blue box in your notes, the one we just wrote down on the previous page, and tell me, how could I rewrite this statement as a statement about logarithms?
Log of 100,000 is equal to 5.
Very good, very good. So we'd have log of 100,000 is equal to 5. And the base of the logarithm here is 10, right? So the base of the exponential is the base of the logarithm. When we say a to the x equals y, that's the same as saying the log base a of y equals x. All right, these are equivalent statements. Let's look at the next one. 2 cubed equals 8. That's a statement about the base 2 exponential. So if I want to rewrite this as a statement about logarithms, it would be a base 2 logarithm. And we would say that the base 2 logarithm of 8 is equal to 3. What about this guy? How could I rewrite this as a statement of about logarithms?
Would it be log base 3 and then in parentheses 1/9 would equal to 2?
Perfect. So the base of the exponential here is 3, so that's the same as the base of the log. And then we'd say that the base 3 log of 1/9 is equal to -2. All right, let's do this last one, and then I'm going to share with you kind of an intuitive way to think about these things. So don't overthink this for now, just look for the pattern. Say which part goes where, like the base, okay, the base goes here. The right-hand side, the output from the exponential, that's the input for the log. And the power in the exponential is the output for the log. So following that pattern, what does e to the 0 equal 1 mean in logarithm form?
Log base e times 1 equals 0.
It's good. Log base e. And be careful with the language. This isn't multiplication. So remember, this is a function. This is like f of 1/9. So we would read that as log base e of 1 equals 0. And that's correct. Okay. There's a couple little details I want to share with you. One of them is just a piece of notation for special bases. And the other one is a sort of intuitive way of thinking about the logarithm. So, no. One way to think about logs is to say that the base a log of some number x, this is the power to which you must raise the number a to get x out. Right? So the base e log of 1, if I wanted to go back from this to this, if I wanted to figure out what the base e log of 1 is, I could say, okay, to what power must I raise e, the base, in order to get 1? Well, e to the 0 is 1, so the base e log of 1 is 0. Or to what power must I raise 2 in order to get 8? Well, 2 to the 3 is 8, so the base 2 log of 8 is 3. Another little bit of notation, some special bases. Special bases for logarithms. There's 2 of them. If you look on your calculator, if you have your calculator handy, odds are you have 2 buttons there for logarithms. One just says log, and the other one says ln. If you're using the base 10, the base 10 log is called the quote common log. And he's denoted by just log of x with no base written. So if you see log with no base here, that means the base is 10. And the base e log is called the natural log. Just like we call the base e exponential, the natural exponential. And he is denoted by ln of x. So base e logarithms are written as ln, logarithm natural log. And the base 10 log is written as just log. Sometimes you'll see it written like this with the block script, and sometimes you'll see it written like this with the cursive script. It doesn't matter, either one is fine. So if I wanted to come back up here, I could rewrite, this all here so you can see. I could rewrite this bottom statement as the ln of 1 equals 0. Because the logarithm with base e is the same as ln. And if I wanted, I could write this top statement as log without any base written of 100,000 equals 5. And those would communicate the same thing. So if you see log without any base, that's the base 10 log. If you see ln, then that is the base e log. Any other time you encounter logarithms, the base will be written explicitly. I'd like to get a little bit of practice just evaluating logarithms, like plugging some numbers into logarithm functions. And then we're going to talk about some properties of the log. All right, now in order to evaluate the log, I encourage you to think of it the way I described in orange on that last page. So let's evaluate the log functions. We're going to look at the base 10 log of 1,000, or I'll just write log of 1,000. We're going to look at the base 2 log of 32. We're going to look at the base 10 log of 0.1. We can look at the base 16 log of 4. And we can look at the, let's see, what else would be fun? How about the base pi log of 1? Okay. Each one of these things is a number. For example, the log log of 1,000, the base 10 log of 1,000, is the number to which you must raise 10 in order to get 1,000 out. So these are all just outputs from different logarithm functions. What is the log, the base 10 log of 1,000? How should we think about that? Put this down here. So the base a log of some number x is the power to which you must raise a to get x out. So in other words here, I'm asking 10 to what power equals 1,000? In fact, if we want to be...
Wait, 100?
You're good. Not quite. 10 to the 100 is a 1 with 100 zeros after it. That's quite large.
10 to the third.
Yeah, good. And I'm glad that we had that little dichotomy there, because the difference between multiplication and exponentiation is something that really pops up here. It's true that 10 times 100 is 1,000, but I'm asking 10 to what power is 1,000? So first, maybe it's worthwhile to say we can rewrite each of these as an exponential statement. If I choose to call this thing x, then this is equivalent to saying 1,000 is equal to 10 to the x. In other words, 10 to what power equals 1,000? And we can think about this one and get ourselves there kind of intuitively. 1,000 is 10 times 10 times 10. It's 10 to the 3. i.e., or thus, the log of 1,000 is equal to 3. All right, so again, when you're asked to just like evaluate a logarithm, I give you the log base something of something else, where both of those things are known constants. Then the way to think about it is, what power of the base will give me the inside? So here the base was 10. What power of 10 will give me 1,000? Oh, well, 10 cubed is 1,000. Okay, then the base 10 log of 1,000 is 3. So you can kind of rewrite it as an exponential statement if you want, and that can help us sometimes. But we want to get to a place where we can just get there by thinking like this. Let's try part B. Let's see if we can find the base 2 log of 32. So again, we want to ask what power of the base gives me the inside? What power of 2 is equal to 32? This could get challenging, right? If the inside is not like an integer power of the base. But I promise for all of these that I'm going to give you right now that they will be. They will be nice, easy problems.
5.
Yeah, 2 to the 5 is 32, right? 2 squared is 4, 2 cubed is 8, 2 to the 4 is 16, multiply by 2 again, and you get 32. So 2 to the 5 is 32. So I would say the base 2 log of 32 is equal to 5, because 2 to the 5 is 32. All right, this one might be a little more challenging. How about the log, the base 10 log of 0.1? So again, I'm asking what power of 10 is equal to 0.1, or 10 to what power is 0.1? It may be helpful to think of 0.1 as a fraction. 0.1, remember, is the same as 1/10. So we're asking what power of the base, which is 10, is equal to 1/10. To what power must I raise 10 to get 1/10 out?
-1.
Excellent, -1. So the log, the base 10 log of 0.1, is the base 10 log of 1/10, because 0.1 is 1/10. And that is equal to -1, because 10 to the -1 is 1/10, or 0.1. It's a slightly new way of thinking. And you need to take the time to condition your brain to this new way of thinking. Pretty much everybody stumbles a bit at first here. But I want you to be brave as we ask these example questions and shut out the answer that comes to mind. If it's wrong, it's wrong. That's okay. If it's right, it's right. That's awesome. But don't stress either way. The best way to get there is just by kind of taking shots at it, letting your brain do its thing, and then slowly shaping your brain into thinking in this new way. This one is not an integer. To what power must I raise 16 in order to get 4 out? So 16 to what power is equal to 4?
Is it 1/4?
Almost. The 4th root of 16 is 2, right? 16 to the 1/4 power is 2. That's going a little bit past where we need to go.
Is it 1/2?
Yeah, 1/2. This is 1/2. Because 16 to the 1/2 power, that's the square root of 16, which is 4. So if we raise 16 to the 1/2, we get 4. It's not so bad, right? It's not so bad. What power of pi is equal to 1? This is a little silly. I'll tell you, it doesn't matter what the base is here. The output for this function, for the log base whatever of 1, is the same no matter what the base is.
I'm gonna go on a guess. Is it 0?
Yeah, exactly, right? Pi to the 0 is equal to 1. So the base pi logarithm of 1 is 0, because pi to the 0 is equal to 1. And this is true for, again, for any base, right? Another way to think about that, a to the x always goes to the point 0, 1. So the log base a of x will always go through the point 1, 0. In other words, the base a logarithm of 1 is 0, no matter what a is. Okay. So this process of just figuring out what numbers are spit out by logarithms is the first thing you need to get comfy with. That's the very first thing that you need to get comfy with when talking about logarithms. And you have a handful of problems in this homework set that ask you to do exactly this, and also ask you to do stuff like this, rewriting the log statement as an exponential statement, or rewriting the exponential statement as a log statement. Take your time on these and make sure that you understand what you're doing there. There's patterns that you will recognize. And once you think you have found a pattern, test it out. See if it works. Try that pattern on the next problem. If it works, that's awesome. If it doesn't work, consider why. See if you can find a different version of it which does. Okay. Now I told you we were going to be using stuff from section 2.8. The primary property of inverse functions is that if you take f inverse of f of x, this always gives you x. And if you take f of f inverse of x, this also always gives you x. So thinking of f of x as the exponential a to the x and f inverse of x as his inverse, which is the base a log of x, we see, and this is our first kind of important algebra property of the logarithm. I'm just going to rewrite each of these statements with these functions. So the first statement here, f inverse of f of x equals x, would be the log base a of a to the x equals x. All right, f inverse of f of x is always equal to x. In other words, the logarithm undoes the exponential. If you plug a number into a to the x, and then you plug that whole thing into the base a log of x, into the base a log, you will get x back out. Sometimes people say this like the log and the exponential cancel, right? In the same way that like a square root and the square cancel. I'm okay with you thinking of it like that. Just be careful and make sure you're using the correct notation. Composing in the other way, we get the same thing. So what is f of f inverse? Well, f would be a to the, and then f inverse is the log base a. So f of f inverse of x would be a raised to the power of log base a of x. This is also equal to x. I'm going to put this in a box also. These are the properties that we use to solve exponential equations and logarithm equations. I use this fact to solve exponential equations, and I use this fact to solve logarithm equations, and we will see that in a minute. As a consequence of these, we can say, actually, let me put it down here. So actually, no, we already said it. So I'll put this over here. Log base a of 1 equals 0 for all a. Do we have an example of this other one here? We don't. Where can I fit this? Around here, don't. Oh, it's okay. We'll save it for later. We'll get it in when it feels natural. Won't force it in here. Okay. So I want to just do a little bit more of this evaluation stuff. A little bit. We're going to evaluate the base 5 log of 1, the base 5 log of 5 to the 8, the base 5 log of 5, and this one looks a little crazy, 5 raised to the power of the base 5 log of 12. So each of these again are numbers. What is the base 5 logarithm of 1?
0.
Yeah, this is 0, right? This is again because the logarithm of 1 for any base is always going to be 0. Think about the properties we just wrote down on the previous page, the blue box statement from the previous page. What is the base 5 log of 5 to the 8? Yeah, exactly, it's 8. And you can get there thinking about it the other way too. To what power must you raise 5 in order to get 5 to the 8? Oh, well, obviously that's 8. What is the base 5 log of 5?
One.
Good. This base, we ask, what power must I raise this base to get this inside? Well, I raise 5 to the 1 in order to get 5. So this is 1. All right, what about this weird one? What is 5 raised to the power of the base 5 log of 12? Yeah, this is a little trickier. So this
12?
number, yeah, very good. It's 12. It's 12. The base 5 log of 12 on its own, that's a nasty, nasty number. I don't know what that is. But 5 raised to the log base 5 of anything would just be that thing. This was the second property that we wrote down on the previous page. Right. I'll annotate these with y. Right. Remember, a raised to the base a log of x, that's always going to be x. And then here, one consequence of this definition is that the base a log of a will always be 1. And we said this on the previous page. The base a log of a to some number will always just be that number. And the base a log of 1 is always 0. So these are some things that you can arrive at by thinking about them carefully. But they're all always true, independent of the numbers involved. So anytime you see a log of 1, that's 0. Anytime you see a base a log of a to some power, that's always that power. Anytime you see the base a log of a, that's always 1. And anytime you see a raised to the base a log of some number, that will always be that number. So these are the sort of things we can simplify very quickly. Okay. We already saw the graph of the base 2 logarithm. So let's look at some transformations. And I'll start just by kind of re-sketching the graph of the parent function here, the base 2 log of x. So just like in the last section, we added some new parent functions to our library. We added all of those exponential functions. Now we are adding all of these logarithm functions, basic logarithm functions, to our parent function library. So if this is the base 2 log of x, then this is 1, 0. This is 2, 1. And over here would be 4, 2. And if you like, down here would be 1/2 comma -1. Right. Here's our regular base 2 logarithm of x. This is what that graph looks like. This is what pretty much all log graphs look like. Right? In that same way that all exponential graphs kind of look the same, all log graphs kind of look the same. I want to use this parent function to sketch these two as transformations. Let's start with the graph of f. What transformation do I need to apply to the purple graph here to get the graph of negative log 2x?
Flip it over the y-axis.
Almost. It is a flip of some sort. Here we're multiplying on the outside. So that's going to be a vertical flip. So it's a flip over the over the x-axis. And if I'm going to flip this thing vertically, that means we're going to flip it about the horizontal axis. So the graph of f here in other words, we're multiplying all the y values on that previous graph by -1. So the point 1/2 comma -1, let me mark off some x values here, 1, 2, 3, 4. I'm going to flip this over vertically. In other words, we're going to multiply all the y values by -1. So 1/2 comma -1 becomes 1/2 comma +1. One comma 0, if I flip that over vertically, if I flip that over the x-axis, stays 1 comma 0. 2 comma 1, if I flip this over the x-axis, if I multiply the y value there by -1, becomes 2 comma -1. Here. And 4 comma 2, if I flip that over the x-axis, if I multiply that y value by -1, I'm out here at 4 comma -2. My vertical asymptote stays x equals 0, but now I approach it up here. And this graph looks like this. So we've flipped the graph over vertically. And this is what we get. So this is the graph y equals f of x, which is negative log 2 of x. And that transformation was a vertical flip. What about the graph of g? What's the transformation I need to apply to the graph of the base 2 logarithm of x to get the graph of log base 2 of negative x? We said this guy is a vertical flip, right? A vertical reflection, because we multiplied on the outside by -1. This guy, I'm multiplying on the inside by -1. What does that do to the graph? If I multiply on the inside of my function by -1. Take a guess.
Are we flipping this one over the y-axis?
Yeah, this is a horizontal flip, right? You multiply on the inside by a negative, that flips you horizontally. Multiply on the outside by a negative, that flips you vertically. This is a horizontal flip. Or I flip over the y-axis. So even without plotting the points, we can just sketch it, right? If I take this graph and I flip it over like this, I'll get a graph that looks like this. Nothing crazy. This point would be -1, 0. That's what I get when I flip 1, 0 over horizontally. This point would be -2, 1. And out here, we would have those big fat points. We would have -4, 2. And we can look at this guy, 1/2, -1. He would become -1/2, -1. This is the graph y equals g of x. G of x was log base 2 of -x. Okay. Got to get comfy with transformations. I don't want to sit here and beat you guys up on this, but you must get comfy with transformations. It's the main tool for graphing, right? You learn your parent functions and you learn your transformations, and then you can graph so much stuff. The main tool for graphing in this class, in Calc 1, in Calc 2, everywhere. Trigonometry, if you're taking trig right now, shifting sine waves left, right, up, down, scaling them, stretching them. It's the main tool for graphing is transformations. We must get comfy with this. We can also shift up and down. We can shift left and right. Let's take a look at one of each of those. I want to begin with a different sort of parent function this time. I'd like to start with a natural log. So we're going to say sketch the functions f of x equals the ln of x plus 1 and g of x equals 2 plus the ln of x from the graph y equals good old-fashioned ln of x. I'm going to give you the graph here of ln x to get started. Ln x is the base e logarithm. It looks a lot like the base 2 logarithm in the same way that the base e exponential looks a lot like the base 2 exponential. We go through the point 1, 0. And we go through the point e, 1. The next kind of nice point out here, if you wanted, would be e squared, 2. But that's way up there. Other points that are on here would be like 1 over e, -1. So I'm just taking that graph of the natural exponential and flipping the points over to get the graph of its inverse, which is the natural logarithm. All right, you need to know these graphs. So here's the graph y equals ln x. Got the point 1 over e, -1, 1, 0, and e, 1. I'll label this one here explicitly. how do I get the graph of ln x plus 1, like the plus 1 on the inside like this, from the graph of ln x? What transformation do I need to apply to this to get this?
Do you move it to the left one?
Perfect. Yeah, Shauna nailed it. Right? We're adding 1 on the inside. That means we're shifting everything to the left by 1. So you want to be a little careful here because our vertical asymptote is going to move. We're going to shift everything to the left by 1 unit. So the vertical asymptote used to be x equals 0. The new vertical asymptote is what? If I take the line x equals 0 and I shift it to the left by 1 unit, what does that become?
-1.
Very good. All right. If I take the point 1 comma 0 and I shift it to the left by 1, what does that become?
Zero comma zero.
Yeah, it becomes 0 comma 0. So this guy's going to go through the origin. Now the other 2 points, their coordinates are going to look a little bit weird, right? Because the x value is an e here. So if I shift this to the left by 1 unit, we're not going to come all the way over here to 1. E isn't 2, it's like 2.7. So that point is going to move to the left 1 unit, which means he becomes e minus 1 comma 1. And my 1 over e comma negative 1, he's going to move 1 unit over. Let's see, I'll draw this in. So we know what this graph is going to look like. All right, we're just taking our previous graph and shifting everything to the left by 1. This guy is going to be (1 over e minus 1, negative 1). Right, so when you shift left by 1, you're subtracting 1 from all the x values. That's all. And this is y equals f of x, which is ln of x plus 1. All right, last one here, g of x equals 2 plus ln of x. What is that transformation?
Move up 2.
Yeah, exactly. This is a shift up by 2 units. So the point 1 comma 0 is going to become the point 1 comma 2. The point 1 over e comma negative 1 is going to move up 1, 2 to 1 over e comma 0. And the point e comma 1 is going to move up 1, 2 to the point e comma 3. This is e comma 3. This is 1 comma 2. And this guy will be the point 1 over e comma 0. My vertical asymptote does not move here. The whole graph just comes up by 2 units. And we get this. This is the graph y equals g of x, where g of x is 2 plus ln of x. All right, graphing these functions as transformations is not anything crazy. It's the same stuff that we've been doing all semester, but we're just using the logarithms as our starting points. You do need to learn these graphs. It is necessary. Before I let you go, because we do have just a couple minutes remaining, I want to evaluate the natural logarithm at a few numbers. Just more practice evaluation. So we'll look at the ln of e to the 8, the ln of 1 over e squared. And we can look at the ln of 1. And then just for fun, how about the ln of 8? Just getting more practice with this evaluation business. How would I find the ln of e to the 8, the natural log of e to the 8? What's the base of the ln? The base of the natural log, the base of ln is e. So I'm asking, to what power must I raise e in order to get e to the 8? If it helps you to write this as log sub e of e to the 8, that's okay. So what is the base e log of e to the 8? To what power must you raise e in order to get e to the 8 out?
8.
8. All right, and in general, the ln of e to any number will just be that number. What about the ln of 1 over e squared?
1 over e.
Careful. So to what power? I applaud the guess, it's good, but think a little bit more carefully. To what power do I need to raise e to get 1 over e squared out? It may help to rewrite 1 over e squared as e to the negative 2. And remember, ln is the same as log base e. So same logic, what would the base e log of e to the negative 2 be?
Negative 2.
Yeah, perfect, negative 2. So the ln of 1 over e squared, or the ln of e to the negative 2, is negative 2. All right, what about this one? This is kind of the silly one. What power of e is 1?
0.
Excellent. All right, now this one down here, 8 is not a nice power of e. So this is not one that you can figure out by hand, not exactly. We know that e is like 2.718281 blah, 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 is pretty close to 3. It's a bit smaller. And we know that 3 squared is 9. So this should be somewhere around 2. But if you want to find the exact value, you will need a calculator for this. It's really not even the exact value. The exact value is just ln of 8. But if you want to write this in a way without using a logarithm, here you will need a calculator. And on your calculators, you have an ln button. I don't have a TI-30 handy. But it's about 2.07, right? Just as we thought, should be pretty close to 2. So we know E is close to 3. So E squared should be close to 9. So the natural log of 8 should be somewhere around the natural log of 9, should be somewhere around 2. And it is. Right? 2.079441. So the only numbers that are nice to plug into the natural log function are powers of E, integer powers of E. And if you plug something else in, you're going to need a calculator. And throughout this section, there will be times when you need a calculator and times when you don't. I am pretty sure that the homework problems I selected for you guys in this first homework set here are all intended to be done without a calculator. There might be 1 or 2, unless it explicitly says use a calculator, do not use a calculator. There's a here. 3. Number E, natural. So 4, yeah, nope. 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 So again, all of this stuff is the same stuff that we've been practicing here, rewriting as logs as exponentials, exponentials as logs. And then there's plenty of this, just evaluate the expression. Right. Okay, so the only ones where you can use a calculator are the problems where it explicitly says to use a calculator. Everywhere else, do not use a calculator. Right? The point here is to practice and come to a place where you understand the logarithms. I know this looks like it has a shitload of problems, but these go really, really fast. So this homework is not going to take you a long time. But I do want you to follow the instructions. If it says use a calculator, go ahead. If it doesn't say to use a calculator, that means explicitly do not use a calculator, and I'll ask you to please honor that. All right, guys, that's where I'm going to leave it for today. Please start trying to get comfy with these logarithms. Next time, we're going to talk about the algebra properties of logs. They have some really funky algebraic properties, kind of similar to those properties we talked about for exponents at the start of section 4.1. And then we're going to move into solving logarithm and exponential equations, which requires use of those algebra properties. Best way to understand the algebra properties, spend the time working on this homework. Make sure you understand how to evaluate logarithms and sort of what the logarithm does with its input. It's a little bit funky. It's a new way of thinking. It's not multiplication. It's not addition. It's kind of the backwards version of exponentiation, which isn't even the same as a root. It's its own new thing. So please practice with that. And next time I will show you exactly how to solve the equation 2 to the x equals 3. It'll be a good day. That's where I'm going to leave it here. Take care, guys. I'll see you next time.